The model for a second-order chemical reaction indicates that the rate at which the reaction is occurring depends on the amounts of two reactants. So what we see here is dx dt is equal to k times the quantity of alpha minus x times beta minus x. And x is the amount of a chemical being formed. We're going to say that that's chemical C. It's being formed from chemicals A and B. Now, there's quite a bit on the screen here. The alpha in the alpha minus x is A times m plus n over m. And the beta in the beta minus x is B times m plus n over n, where A is the amount of chemical A, B is the amount of chemical B, and m parts of A combine with n parts of B to make chemical C. Let's unpack this a little bit. If I've got A and B and they're combining to make C, if we've used m parts of A and n parts of B, then altogether the amount of C is given by m plus n. So proportionately, in C, we have m divided by m plus n from A. And then n out of that m plus n is from B. This might be a little easier if I use some numbers here. Suppose we've got like 3 parts of A and 2 parts of B are going to combine to form C. Then C comprises that 3 plus 2, or 5 parts total. Of those 5 parts, 3 came from A. Of those 5 parts, 2 came from B. Now these are proportions. So if we're making chemical X and we've used A and B, then m over m plus n of X came from A. If we started with A grams, then we have A minus that ratio m over m plus n times X of chemical A remaining. Likewise, if we started with lowercase b grams of chemical B, then B minus n over m plus nx is how much of B is remaining, because the proportion of X that came from B is n over m plus n. So putting that in the context of the rate of the chemical reaction, the amount remaining of chemical A and the amount remaining of chemical B times a constant of proportionality is going to give us the rate of reaction dx dt. Now, if we factor out m over m plus n from the first set of parentheses and n over m plus n from the second set of parentheses, we can rewrite the differential equation into the form that was originally given, which was k times alpha minus x times beta minus x. Of course, these two k's are different, so I'll take the previous k and I'll make it k1 or something like that. But really what this is k times the amount of chemical A times the amount of chemical B. And from that factoring, we have that alpha is equal to A times m plus n over m, and beta is equal to B times m plus n over n. And we're going to put all this into context in this example. Two chemicals, A and B, are combined to form a chemical C. The rate of the reaction is proportional to the product of the instantaneous amounts of A and B not converted to chemical C. What that tells us is that our model is dx dt is equal to k times alpha minus x, beta minus x. Initially, there are 80 grams of A and 50 grams of B. So lowercase a equals 80 and lowercase b equals 50. For each gram of B, 2 grams of A is used. that tells us that m is equal to 2 and n is equal to 1. We'll get to the rest of that text in just a moment. But for now, the only other thing we need to know is remember what alpha and beta are. Alpha is a times lowercase m plus n divided by m, and beta is lowercase b times m plus n divided by n. Since m plus n is 3 and a is 80, we have 80 times 3 over 2 is equal to alpha, so alpha is 120. Beta is equal to 50 times 3 over 1, not very exciting, but 150 there. From this, we can flesh out our differential equation. Dx dt is equal to k times 120 minus x times 150 minus x. Again, this isn't linear, but it is separable. So we've got dx divided by 120 minus x times 150 minus x is equal to k dt. We're again going to use partial fraction decomposition. We get the integral of 1 over 30 divided by 120 minus x minus 1 over 30 divided by 150 minus x times dx is equal to the integral of k dt. Integrating and then making sure that we're careful about negatives because of the substitution rule is going to give us 1 over 30 times the natural log of the absolute value of 150 minus x divided by 120 minus x is equal to kt plus c. I'm going to clear the fraction of 1 over 30, and it's not going to have much of an effect. It's just really a cosmetic effect on the right. On the left-hand side, we have natural log of 150 minus x over 120 minus x in an absolute value. And on the right-hand side, I'm just going to call this k1t plus c1. Why not go back and change the previous steps? Because we're going to find numbers for these right now, and so it doesn't really matter. I'm not looking for a pretty presentation with these constants. I am looking for an initial condition, though. It's observed that 10 grams of C is formed in 10 minutes. And then we're asked for some information about how much is formed in 40 minutes and what is the limiting amount of C after a long time, how much of chemicals A and B remains after a long time. We'll come back to all of that. If 10 grams is formed in 10 minutes, then we know that x of 10 is equal to 10 because x is the grams of C that's formed. But we have two unknowns, K1 and C1. We need to make an assumption at this point. We're going to assume that at the beginning of the process, when the time is 0, no grams of C have yet been formed. So x of 0 is equal to 0. And using that, we're going to get that C1 is equal to the natural log of 5 over 4. Using that and then exponentiating both sides to get rid of the natural log, and then using a property of exponents on the right-hand side, we get 150 minus x divided by 120 minus x is equal to 5/4 times e to the k1t. And here we can use x of 10 is equal to 10. So the x of 10, the 10 inside the parentheses, is 10 in place of t, and the x of 10 equals 10, the 10 on the right, is 10 in place of x. Using that, we get that k1 is equal to 1/10 times the natural log of 56 over 55. Okay. How about if we say it's approximately 0.0018? Then clearing the fraction and collecting x on one side, factoring out and dividing will ultimately give us that x of t is equal to 600 times e to the 0.0018t minus 1 divided by 5e to the 0.0018t minus 4. I kind of crammed that in there and didn't need to. There's our model. How much is formed in 40 minutes? Well, that's going to be x of 40. That is totally a calculator exercise. I get about 4.2 grams. after a long period of time. So we're looking at, say, the limit as t approaches infinity of x of t. This is not the most useful form of a solution to determine that, but we can see that the e to the 0.0018t is in both the numerator and denominator. As t goes to infinity, those exponents are both going to blow up, but at the same rate. So the -1 and the -4 don't really matter, and all that matters is the 600 over 5. So we can see that this limit is going to be 120. We'll call it grams. Another way to have dealt with that would be to multiply the numerator and denominator by e to the negative 0.0018t. Doing so would give us 600 times 1 minus e to the negative 0.0018t divided by 5 minus 4 e to the negative 0.0018t. This is just a little bit easier for me to think about because now I can see the exponential has a negative exponent as t goes to infinity. Both of those terms are going to end up going to 0. We still have the same result of 600 over 5 giving us 120 grams. Now the last bit for this problem, how much of chemicals A and B remains after a long time? We started with 80 grams of A and 50 grams of B. These would combine to make 130 grams, except it's not the case that all of A and all of B are both used. Remember, we were told for each gram of B, 2 grams of A is used. So if I've got 50 grams of B, in order to use up all of that, I need 100 grams of A. I don't have 100 grams of A, I have 80 grams of A. So if we use 80 grams of A and 2 grams of A are used for every gram of B, then we're using 40 grams of B. That's how we're going to add up to 120, which means 10 grams of chemical B are left over. Furthermore, we can see that A is the limiting factor in this case.